Last time what we learned is on a T versus lowercase s diagram, the area under the curve is equal to Q over M, heat transfer per unit mass. Now let's apply what we learned from last time to Carnot power cycle. Okay, what is a Carnot vapor power system? It is just a power plant where you have a boiler and then the steam turbine. After the steam turbine is a condenser, and then after the condenser you have a pump. Okay, and then what we did is to sketch the process on a P versus nu diagram. P versus nu diagram. And first of all, vapor dome. And then on the vapor dome, we have two constant temperature lines. Curve down, go straight, and then curve down. Okay, the top one is T hot, temperature inside the boiler. Bottom one is TC, temperature in the condenser. Okay, if you forgot about this, you can go back to our videos. Okay, so 4 to 1 is the boiler. Number 4 is usually saturated liquid. And then goes to number 1. 4 to 1 is in the boiler. 4 to 1 goes to the right. Number 1 is the exit of the boiler, which becomes the saturated vapor. And then 1 to 2. 1 to 2 is the steam turbine. That's adiabatic expansion process. So curve down. We explained it already before. Number 2, curve down. And then 2 to 3 is the condenser. You move to the left. That's number 3. Number 3 is the exit of the condenser. And 3 to 4 is the pump. Go up and to the left. And then we said before, the area of the enclosure tells you one thing on a P versus nu diagram. If you forgot, you can go back. And we told you area of the enclosure is equal to W cycle per unit mass. And we know W cycle is equal to work generated by the turbine minus work consumed by the pump. WT minus WP. Okay, and then we said the good thing about this is we can visualize work, W cycle. It's just the area of the enclosure. But the downside is we cannot really calculate the value because 1 to 2 is a curve and 3 to 4 is also a curve. So this is an irregular shape. We cannot calculate the area of an irregular shape. Okay, and then we said we introduced a new diagram. It's called T versus S diagram. Let's see if this new diagram can help us. Y coordinate is T, temperature. X coordinate is lowercase s, specific entropy. Let's recall you still have a vapor dome. And then you still have two constant pressure lines. Curve up, go straight, and then curve up. Curve up, go straight, and curve up. Okay, so those are two constant pressure lines. The top one we should call it P, maybe high, pH, and the lower one we should call it PL, P low. So the pH is the pressure inside the boiler, and PL is the pressure inside the condenser. Okay, let's start from 4 to 1. 4 to 1 is in the boiler, and it's a constant pressure process. So 4 to 1 must be on pH line. And what is number 4? Number 4 is still point F, so we locate number 4 here. And where's number 1? Number 1 is still saturated vapor, so number 1 will still be here. 4 to 1, same as before. Okay, 4 to 1, still the boiler. The next one, let's sketch 1 to 2. 1 to 2. Okay, 1 to 2 is the steam turbine. Let's recall 1 to 2. Process 1 to 2. 1 to 2 is the steam turbine. And the name of the process is adiabatic expansion. Okay, remember the keyword adiabatic. And then don't forget, this is a Carnot power cycle. What does Carnot give you if you can remember? The definition of a Carnot cycle is you have a series of 4 steps and each one of them is reversible. So if you see the word Carnot, think of the word reversible. Every step is reversible. So now you have adiabatic plus reversible. Can you recall what we call it? If the process can satisfy those 2 requirements, first one adiabatic, second one reversible, what do we call it? Let's go back if you forgot. Here, if the process is adiabatic and also reversible, then this process is isentropic. And what's so nice about isentropic process? Entropy does not change. Okay, so now we do satisfy those 2 requirements. So what we have here is actually an isentropic process. And if it's isentropic, delta S is equal to 0. So now for process 1 to 2, entropy is constant, and entropy here is my x-coordinate, so that means my x-coordinate is constant. If the x-coordinate is constant, then it must be a vertical line. So 1 to 2 here on a t versus s diagram must be a vertical line. Do I go up or go down? Go down, because this is an expansion process. Pressure becomes lower, so I need to go down to P low, PL. So we go straight down. Okay, so this time 1 to 2 is a straight line going down. Number 2. Okay, and then 2 to 3. 2 to 3 is still the same. It's gonna be on PL line. PL is the pressure in the condenser, and 2 to 3 is the condenser. Do I go to the right or to the left? To the right or to the left, what do you check? You check the x-coordinate, which is entropy. 223 is the condenser. That's where you lose heat. Do you remember, if your system loses heat, you also lose entropy. So that means entropy becomes smaller. If your x-coordinate entropy becomes smaller, you need to move to the left. So 223 to the left on a horizontal line. Okay, and then let's recall process 324. What is process 324? 324 is the pump. And what's the name of this process? It's adiabatic compression. And again, let's recall this process is Carnot, which means every single step is reversible, including 324. Adiabatic plus reversible. So we can call this process isentropic. And what's so nice about isentropic? Entropy does not change. So for process 324, entropy is constant. Entropy is your x-coordinate. So again, your x-coordinate is constant. If your x-coordinate is constant, it must be a vertical line. So that's why 324 must be a vertical line. Okay, so that's the process. 421 is horizontal, 122 is vertical, 223 is horizontal, and 324 is vertical again. So you can see the shape of this enclosure 41234 is actually a rectangle. Does that help us? Let's take a look. Let's continue. Let's recall from energy balance equation. Total energy going in, which is Q hot, must be balanced by the total energy leaving. Total energy leaving is W cycle and QC. So from here, we can rewrite W cycle. W cycle can be rewritten to QH minus QC. QH is the heat you gain from this process. Where do you gain heat? You gain heat in the boiler, and the boiler is 421, so we change the subscript to 421. Minus QC. QC is the heat you lose in this process. Where do you lose heat in this process? The condenser. And the condenser is 223, so we change the subscript to 223. Okay, and now let's continue. We divide every term by mass. So left-hand side becomes W cycle per unit mass. Right-hand side becomes Q421 per unit mass minus Q 223 per unit mass. And again, let's recall, if you have a t versus lowercase s diagram right here, t versus lowercase s diagram, the area under the curve is equal to heat transfer per unit mass. So here, heat transfer per unit mass is equal to area under the curve. Area under the curve 421. Same thing happens to the second term, minus area under 223. Okay, let's take a look. Area under 421, where is that? Let's go back to our diagram. Area under 421. You can take a look. Area under 421 is here. It's a rectangle. That's area under 421. Okay, and then what we do is subtract minus area under 223. Minus area under 223. Let's use a different color. Minus, so we subtract the area under 223. Subtract the blue. So red minus blue, what is left? What is left is the area of the enclosure, 4, 1, 2, 3, 4. Okay, so now we can say the area that is left is the area of my enclosure. We proved it from geometry. It's equal to the area of the enclosure. So now what's our conclusion? Area of the enclosure on a T versus S diagram is again equal to W cycle per unit mass. So we can write down our conclusion here. Area of the enclosure is equal to W cycle per unit mass again. So now let's take a look. If you have a P versus nu diagram or a T versus S diagram, the area of the enclosure tells you exactly the same thing, which means W cycle per unit mass. Okay, but one thing I want to point out here is if you have a P versus nu diagram, like here, P versus nu diagram, the area under one single curve is work per unit mass. And on a T versus S diagram, the area under one single curve gives you actually heat transfer per unit mass. But then when you go to the area of the enclosure, they tell you exactly the same. Doesn't matter which diagram you're on. It's either P versus nu diagram or T versus S diagram. They all tell you the same thing, that is W cycle per unit mass. And now you should realize why we prefer to have T versus S diagram. Why? Because not only we can visualize W cycle per unit mass because it's equal to the area of the enclosure, but also we can actually calculate the area of the enclosure, which means we can calculate W cycle per unit mass. Why can we calculate it? Because in this case, on the T versus S diagram, the enclosure is actually a rectangle, and we can easily calculate the area of the rectangle. It is height multiplied by the length. That's it. Okay, so now let's do that. How do we calculate the area? Let's continue. How do we calculate the area? W cycle per unit mass, we know, is equal to the area of the enclosure. And this enclosure is a rectangle on T versus S diagram. Okay, how do we calculate the area of a rectangle? height multiplied by distance. What is the height of this rectangle? Let's say this one, we call it T hot. This is the temperature in the boiler. And then the y coordinate of point 2 or point 3, we can call it T cold. That is the temperature in the condenser. And then the x coordinate here, we can call it either S1 or S2 because it's vertical, but we prefer S1. Why? Because point 1 is just point G, and we can easily find SG from the table. And then the x coordinate here, we can call it S4 or S3. It's up to you. They are equal because 3 to 4 is a vertical line. But usually we prefer S4 because point 4 is F point, and we can easily find SF from the table. Okay, so now what is the height of this rectangle? Is TH minus TC. That's the height. And what is the base of this rectangle? It's S1 minus S4. So in total, the area is height multiplied by base. Height is TH minus TC. TH is the temperature in the boiler. TC is the temperature in the condenser. Multiplied by S1 minus S4. That's it. So now we said we can not only just visualize work per unit mass, we can now calculate the value. Okay, so now one last thing is last time, a few weeks ago, we told you if you have a Carnot cycle, eta must be equal to eta max, and eta max is equal to 1 minus Tc over Th. We never proved this equation. Today, finally, we can prove to you this is true. So here is the proof. Let's start from the definition of efficiency. The definition of efficiency is what you get divided by what you pay. What you get is W cycle, the electricity coming out of the power plant, divided by what you pay. What you pay is the heat you burn from the gas to get the heat. Okay, and then from energy balance equation, we know W cycle can be rewritten to Q hot minus Q cold over Q hot, which becomes 1 minus QC over QH. And again, we do the same thing. We change the subscript. QC, losing heat, that's the condenser, so process 223. Q hot, that's gaining heat. You gain heat in the boiler, that's 421. And then we do a math trick. What we do is to divide both of them by mass. Okay, and then let's recall on a T versus S diagram, the area under the curve is equal to heat transfer per unit mass. So we can rewrite the numerator and the denominator into area. So the numerator will be rewritten to area under 223. And the denominator will just be equal to area under 421. So now let's continue. Take a look. What is the area under 223? Let's go back to the T versus S diagram on the right. What is the area under 421? The area under 421 is, it has a height of TH, and it has a base of S1 minus S4. So the area under 421 can be calculated by the height, which is T hot, multiplied by the base, which is S1 minus S4. And now let's take a look. Area under 223, how do we calculate that? Go back to the diagram, take a look. Area under 223, it has a height of TC, and it has a base of S1 minus S4. So the height multiplied by the base is TC multiplied by the base, S1 minus S4. And now you can tell S1 minus S4, they cancel. So the only thing that is left is 1 minus TC over TH. Left hand side still eta. So now we proved it. If you have a Carnot cycle, maximum efficiency is equal to 1 minus Tc over Th. And when you plug in temperatures, make sure you always use Kelvin to avoid any mistake.